तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We have been discussing the MSI and LSI circuits and implementing combinational logic using these circuits. We talked about multiplexers, decoders and programmable logic devices, PROM, programmable logic array, PLA and PAL, programmable array logic. But as you know that most circuits are sequential in nature, and even the combinational logic we discussed are useful in steering the combinational sequential circuits through the various states as per the state diagram, state graph. So basically when you design a circuit or a subsystem or a system, whatever you want to call it, whatever level you want to deal with, it is a sequential circuit. When you say sequential circuit, it does not exclude combinational, whereas when you say combinational, it excludes sequential. That is why when I say sequential, I do not have to say combinational and sequential, I do not have to say that. Sequential circuit will have to have a combinational logic, which will be the logic for determining the next states and the outputs. So with that in mind, we will now look at the implementation of sequential circuits using same MSI LSI logic. Instead, I want to again emphasize this point once more, that when I say sequential circuit, it has a combinational and a sequential component. So the combinational part will use all this MSI LSI we discussed. Of course, you will also see that we can also do sequential. For example, the programmable array logic we saw had its own what? Flip flops. That is what we discussed last time, and those can be utilized for the sequential part of the circuit steering logic, or that is state, to implement the states. So it is a combination, the integrated effort. Second thing is we will also see later on how some of the sequential MSI like a 4-bit counter or a shift register can also be used for implementation of circuits, state graphs. We will see that after this. So right now we will use the same multiplexer, decoder, etc., and take a state graph which you know how to implement otherwise using gates. You will take such a circuit and see how to implement it using some of those MSI LSIs we learned in the last few lectures. So for that we will take an example state graph, a sample state graph as example. You know what this means, this interpretation of this graph. One input, one output, and this has 5 states, and this is a Mealy machine or a Moore machine? It's a Mealy machine. Machine with 5 states, S0 through S4. You have to make sure that each of these states has 2 arrows going out. One is for 0 input, the other is for 1 input. So S0 when 0, it goes back into this. So 1 it goes here. S1 is 0, it goes here. So 1 it goes here. S2 is 0, it goes here. 1 it goes here. S3 0 goes back. 1 it goes here. S4 0 goes here, and 1 it goes back in the same state. So this, as I said, is an arbitrary state graph. A sample state graph, state diagram. I want to use this diagram to illustrate the point of how to implement this using multiplexers, proms, PALs, PLAs, etc., which will be used as steering logic, and in case of PALs will also flip flops also will be used from the same IC. So first, well, again there is no, we don't know the system, it's an arbitrary graph. We are assuming there is an input and an output, so we will call the input X and output Z. See XC here, this is input, this is output. And there are 5 states, so we will call the states S0, S1, S2, S3, S4 as arbitrarily 0, 0, 0, 0, 0, 1. We are not using any assignment rules. We also should have names for state variables. We will call the state variables ABC. 3 state variables, we will call them ABC. There are 5 states, so ABC goes through 0, 0, 0, from 0, 0, 0 through 0 through 1, 0, 0. So you know how to draw. Let us use D flip flops to make the implementation simple, in the sense that you don't have to go through the state table and then a transition table. State table and transition table are same for a D flip flop implementation. We know that. So we will take this and write the table or state table, which is also the transition table for this diagram. So the present state, what are the various things you will write in the state table? The present state, input X, present state variables are A, B, C, input variable is X, then the next state is ABC. To distinguish between this ABC and this ABC, we will put a plus sign here, meaning the values of ABC after the clock pulse, and then the output C So, let us quickly write this from S0, x can be 0, x can be 1, is it not? Then from S1 it can be 0 or 1, at S2 again it can be 0 or 1, S3 input can be 0 or 1, S4 S5, S6, S7 do not exist. So, is 1 0 1, 1 1 0, 1 1 1 do not have these states, so there is no need for considering the input x 0 input x 0 1 for these states. So, can somebody quickly tell me, so you do not have to make mistakes, so that you will not make mistakes. Now, tell me what is S0 go, where does S0 go from x when x is 0? S1, it's same state, 0 0 0. Output? Next. Say it. 0 0 1 0. Then 0 1 0 0 0 1 1 0. Is that right? That is when S3 is S1 circuit is in S1, input is 1, it goes to S3 which is 0 and 1, output is 0. Then from S3, from S2 it is 0 0 0, output 0, or 1 0 0 with an output of 0. Then from S3, if it is a 0, it goes back to reset state S0. So 1, it goes to S4 with an output of 1. Is that right? And from S4 it is going back to 0 1 1, output of 0, but it remains in that state, output of 1. Is that right? This state table is also act as a transition table because we are going to use D flip flops. And these states are not going to appear, so the next states are also not defined, don't care. But the outputs are always zeros. Whenever the state is not defined, make the output 0. It is also possible in advance, this is an elementary level of treatment. So, slightly more advanced level we can say when the state transition has to happen, there also when so don't care state occurs between two states whose output is 0 or two states whose outputs are 1. By making it a 0, we are causing a glitch. Do you understand what I am saying? Suppose I had a state and the next state is I don't care, and then another state. In both these states, defined states, the output is 1, and in between the don't care state, the output is, because we said all don't care state make the output 0. If that means I will force an output of 1 to become 0 and then back to 1. If I can retain that 1 as 1, then I will avoid a glitch. So that is a special technique. So as I said, we are treating this, we are keeping this discussion elementary because this is an introductory course on digital. I would rather teach you concepts and some of those practical things. Of course, I have been mentioning here and there, like optimizing the state graph, assignment rules, reduction of the state graph, some of those things, assigning output states properly. This will these are topics which I thought you should know that exist. It is not that people don't think about these things, but some of those things you can learn a little later once you are familiar with the basic things. These are things which come when you do practical design. Anyway, coming back to this, we will put all outputs 0 to start with now. As for now, we will use the standard rule we have been following, that all outputs of undefined states will make them as zeros. So, the question is, now I do not want to go through the Karna map, Karna map minimization of this is what A plus B plus C plus are the inputs to D flip flops, isn't it? In the case of a D flip flop implementation, this becomes the D flip flop input for A, D flip flop input for B, D flip flop input for C, and this is the output. So, we will have to draw Karna maps for each one of them and simplify it and then implement it using gates. This is the procedure we are familiar with. Now, I am going to introduce multiplexers in the place of the combination logic which we have earlier done using gates. Let us try to do a multiplexer based implementation. I will still need D flip flops because multiplexers can only give you the steering logic. Multiplexers are combination logic blocks. Remember that multiplexers are combinational building blocks, and combinational building blocks is only a logic which controls the state variations, state transitions of the flip flops. So, that I am going to replace by multiplexers, but does not mean that I am going to eliminate the D flip flops. So, D flip flops remain. So, the circuit is going to look like this, a mux based implementation. We are going to have 3 flip flops. D flip flops, these 3 flip flops gives the state variables A, B, C. There is no change in that. That is what we have been doing, that is what we have been following. This rule will continue that, and then this will be driven by clocks of course. So, my aim is to reduce the combination logic ICs used, number of ICs used in combination logic. Instead of having a variety of gates of different types, can I use multiplexers and get this? That is my question. So, the DA which is the input to the A flip flop, DB which is input to the B flip flop, DC will now come from multiplexers instead of gates. That is the earlier we have done the same problem, I mean not the same state graph, we might have similar and we know how to get DA, DB, DC by drawing Karna maps and simplifying them and drawing a gate implementation. Is that correct? Now, I am going to use multiplexers to get DA, DB, DC. The output of the multiplexer should be connected to DA, another output of another multiplexer to BB, output of another multiplexer to DC. That means that we need 3 multiplexers. So, very simple system design. This board is not big enough, so I will have to draw them rather small, but it does not matter. So, this is the output of the first multiplexer, this is the output of the second multiplexer, this is the output of the third multiplexer. So, each of these is a 8 to 1, okay, 8 to 1, I will not say 8 to 1, now I will tell you why it is 8 to 1. 8 to 1 because there are 8 different states in which the circuit exists, of course 5 only we will use, 3 I do not care, but possibility of 8 different states, and when you are in the present state we want to know what is the next state, that is all there is in the steering logic. What is the purpose of steering logic? Given the condition of the present state and the input, what should be the next state, and next state is nothing but DA, DB, DC values for the next state. That means I give the present state values along with the inputs and find out what should be the next state, isn't it? So, multiple 8 different present states are possible, and each of the present states what should be the next state. So, the multiplexer is a selector mechanism I can have the selected signals as the present state and the corresponding input will be connected to the output. Suppose you have a 4 to 1 mux, you have 2 selectors and 4 inputs. So, the selectors are 0 0, first input will be connected to the output, the selectors are 0 1, second one will be connected, so 1 1, the last one will be connected. We will use the same argument here and say I am going to give the values of the present state, the ABC which is available here. These are the selector values S2, S0, S1, S2, S1, S0, S2, S1, S0. To this we will connect this ABC. So, it is going to be very messy if I draw that. So, you can just assume that this is ABC which are coming from here, this A, this B, because these are the present state values which is fed back. You remember that overall block diagram of that sequence circuit implementation. We have this steering logic, the output which is the next state variable which is kept in the flip flop, fed back as the present state along with the input, and then you get the next state. Imagine that, visualize that block diagram. So, ABC has to go back into the combination logic, isn't it? That is what this is, this ABC. So, this is ABC. Now, all you have to do now is to look at this state table, find out what the corresponding present state 0 0 0 corresponding to present state 0 0 0, what should be DA, what should be DB, what should be DC. If X is 0, if X is 0 to 1. If I can put that information in the input of the multiplexer, ABC being selected now 0 0 0, that will be connected to DA, and so we will go to the next state required, next state. Now, as an example, we will take the first row. So, the present state is 0 0 0, X is 0, the next state of the flip flop A should be 0. If the present state is 0 0 0 and the input is X is 1, then also the next state of the flip flop is 0. So, the next state of the flip flop A should be 0 when the present state of the circuit is 0 0 0. The circuit is in S0 state. The circuit is in S0 state, that is 0 0 0 state. The next value for A is 0 irrespective of the value of what? X, irrespective of the value of X. Because of that, if I can put a 0 here at the first input, how many inputs are there for this? 8 to 1 multiplexer, there will be 8. So, this is, we will call this I0 to I7, 0 I1, I2, I3, I4, I5, I6, I7. 1, 2, 3, 4, 5, 6, 7. That is why it is an 8 to 1 multiplexer. That is why each of these is an 8 to 1 multiplexer. There are 8 possibilities, and each of the possibilities should select the next value. Now, let us finish flip flop A before going to flip flop B. So, we can exhaust this column, then go to this column, then those. You can do it either way, does not matter. I can draw parallelly A, B, C and then go to next state, does not matter. It is more convenient to look through this and then this and then this. So, the present state variable is 0. I mean the present state is 0 0 1, then S1 is S1 state, again irrespective of the value of X, the next state is a 0. Next state is a 0 irrespective of the value of X is X if the present state of the flip flops are A 0 0 1. So, again put a 0 here. Now, you know how to do this, it is a simple game we are playing, that is all. So, I am giving you a procedure where implementation is the minimum thing. So, all you have to do is to concentrate on the state graph. Again, I emphasized this point earlier. As an engineer, you are responsible for this proper state graph, most efficient state graph. After that procedure, either it is a manual or a software. and then there is the hardware which can be mapped and all that type of thing, which is technician's job. Of course, I am not demeaning the job of technician. In fact, they are better than you in the sense your circuit will work on paper, their circuit will work on hardware. They have to build it and test it. But still, what I am saying is, as a design concept, if you are a designer, a company hires you for designing digital systems, what maximum contribution comes in the interpretation of the problem into a state graph. Rest is a routine procedure. I am not saying it should not be done, it should be done, it should build it and test it. If it does not work, you have to change it and all that type of thing. So, go again, S2, it follows X. If X is 0, the next state is 0, X is 1, next state is 1. That means if the current state is S2, the next state is of flip flop A is 0 if X is 0, 1 if X is 1. That means I need to connect X to the third input. This X is not, don't care, this is X input. S3, same, follows X. Next state variable follows the input. That means it is X again. S4, present state is 1. I don't know why, I just arbitrarily took this example. I just drew a map and it so happens that S3 again, S4 again the same thing. Circuit is 0, 0, circuit is 1, circuit is in state 1, 0, 0. If X is 0, the next state is 0 for A. X is 1, next state is 1. So, it is again X. So, first 2 zeros, next 3 X's, and these 3 are don't cares. Isn't it? So, don't cares, don't confuse this, don't cares. So, I will put a D or a phi here. You know. Some people use phi in don't care state. Some people put a 0 there. 0 should not be put because you have a 0 logic. So, I will put a D also if you want. X is used, but then since I already used as X variable, so I want to use it as a D, don't care variable. So, first 2 inputs have to be tied to 0, next 3 inputs have to be tied to 1, X, the input X, and the last 3 input can be tied to anything, it can be 1 or a 0. Let us do this for the next one. So, I will only concentrate on 0, 1, 2, 3, 4, 5, 6, 0, 1, 2, 3, 4, 5, 6, 7 are anyway, don't care. Is it not? 5, 6, 7 anyway, don't care. So, what is I0 to I4? Now, we have to look at the second column, flip flop B column. Present state is 0, 0, 0, next state is 0 irrespective of the value of flip X. X is 0, next state is 0, X is 1, next state is 0. Second state, circuit is in S1 state, and you want to find out the next state of the flip flop B. It is always 1. Next state of the flip flop B is 1 from the present state S1, whether or not X is present or not. X is present. So, that is a 1. So, what should be the next one? 0. The circuit is in S2, irrespective of the value of X, next state of flip flop B is 0. S3, same. S4, X bar. The circuit is in S4, if the value of X is 0, next state of flip flop B is 1. The value of X is 1, the next state of flip flop B is 0. That means the complement of X. So, next bar. So, tie the first 1, 3, 4 to 0, second one to 1, and the fifth one to X bar. See, the design is so mechanical, that means this is common for whatever. If my state graph changes, the only thing will change is this. As long as there are up to 8 states in my circuit, in my state diagram, it is a common circuit diagram, is it not? This circuit diagram is common up to 8 states. Only thing will be different from, it will be different, that will be different from design to design is the set of input variables, inputs that you need to connect for each of these multipliers. There again the elegance is there. This is a very elegant circuit implementation. A number of ICs, only 3 muxes, not a whole lot of gates, even though these muxes are functionally more complex. As I said, the cost wise and everything else they are comparable, so we do not have to worry about having to use a multiplexer instead of a gate. Come on, let us finish this. The next is what? The last 3 is again do not care. So, I0 to I4, 1, 2, 3. Present state 0, next state value is same as the input value. Present state 0, 0, 0, next state of C is 0, x is 0, 1 if x is 1. So, this has to be a what? X. Next is x again because of this. X value is reflected. C plus follows x if the circuit is in state S1. So, it is x. Next is 0, next is 0. Sorry. Finally, it is x bar. If the circuit is in S4 state, output is 0, 1. The input is 0, the output is 1. I mean, x is 0, the next state is 1 for C. If the input is 1, next state is 0 for C. So, it is x bar. Why don't you say with conviction so I can be confident that I am not making a mistake here when I am drawing. See, I have to do mapping from here to here, surface, horizontal mapping from here to here to here. It is not easy when you stand so close to the board. So, sometimes you tend to miss something. So, when you say resounding, yes, then I know that I have not made a mistake. That you do not lose anything. Had breakfast this morning? No? There is no answer. I do not know what to take it as. Anyway, so we have finished this implementation, and then the output is not been completed. Output is to, again you draw a corner map for output, you know. You can do that if you want to. You can draw a corner map because there are only how many entries of 1? There are only 1, 2, 3, 4 entries of 1. Rest are 0. I can draw a corner map and make a simple gate circuit, but if you want to use any multiplexer, it is fine. I can give you a multiplexer based output also. Z comes from the same, if you give the same input variables, A, B, C, to this 8 to 1 max, the output can be, output of the multiplexer can be my output of the circuit C. Again, depending on what present state the output is. The output is determined by the present state and the input variable, is it not? Output is determined by the present state and the input variable. In S0 state, if x is 0, the output is 0, x is 1, the output is 1, like 0, like that, it goes. So, I can use the same technique of drawing the multiplexer based output. So, there will be I0 to I7, 2, 3, 4, 5, 7, 0 for this state, 0 for this state, 0 for this state. First 3 outputs are 0 anyway. For the first 3 states, whether or not x is 0 or 1, whether or not x is 0 or whether or not x is present, output is 0. Fourth state, that means S3 state, if the input is 0, the output is 0, if the input is 1, the output is 1. So, I need to put a what? X. The fifth state again, S4 state, again the same thing. If the input is 0, the output is 0, input is 1, the output is 1, X. And we assume that the last 3 will be don't care, so we will put zeros. Anyway, you don't put D. You can put D, I am just saying it is a general practice. Because if you have a state momentarily going through that state and an output is a 1, when you do not require an output, some glitch may cause some triggering something. But it is only a practical tip. Design completed. flip flops driven by muxes instead of flip flops driven by D flip gates. This is how I used the MSI to implement that. Yes.
So would the output correspond to the previous state or
No, the output according to the state graph, the output is defined by the present state and the input. If the circuit is in S0, this is what the next state is. When the circuit is in S0, let us take this state. Circuit is in S3, its input is 0, next state is S0. This arrow means from S3 it goes to S0, not now, at the next clock edge.
but the output
Wait, I am coming to that. But in S3 the output is defined as 0 if x is 0, 1 if x is 1. In this output corresponds to this state. Because the difference of a million more, what did you say? More machine, the output is defined for the state. In the S3 state the output is defined. If it has been a more machine, I will put a 0 here. Let us say this also 0, this one. Put a 0 here. In a milli machine, we are saying the present state alone does not determine the output, the present state and the input determine the output. So, the output corresponds to the present states, not to the next states. This is a confusion sometimes people have, and some of the books do not explain this very well. It is a present state output we are defining. Is that clear? Right. Good. So, and I now use a ROM instead of a mux, PROM. That is even easier. There are 4 outputs which are DA, DB, DC and Z. How many inputs? 4 inputs. I need this can be considered as a truth table for a PROM implementation. What is the size of the PROM? This is the address. Inputs of the ROM is called address. I told you this. Address. That means to tell you what has to be stored in each of these locations in the ROM. There are 4 addresses, that means there are 16 locations. I need a size of 2 power 4. First of all, write size is 2 power 4 times 4. Don't write 2 power 4 is 16, so 16 plus 6 times 4 is 64 bits. So the answer is right, but not practical. If you buy a 64 bits ROM, it doesn't have 4 inputs and 4 outputs, I can't implement the circuit, right? So this is the size of the ROM that we need, PROM we need, and the outputs are, see, it goes into the 3 flip flops. I will not draw separately, just you know what I mean. 3D flip flops, and the outputs are, this is a standard block diagram of a sequential machine. Each is a flip flop, all clocked at the same time, so I am combining. You can also use a 4-bit register and use first 3 bits, that is also possible. You need not be 3 individual flip flops. For example, flip flops come in dual. I told you 4 to 1 multiplexers come in a dual chip. You cannot buy a single 4 to 1 mux. You have to buy a dual 4 to 1 mux and use one. If you want to buy an inverter, you have to buy 6. 6-pack they call it in US. If you want to go beer, buy, you have to buy 6-pack, right? Price is cheaper. Of course, they will sell individual, but then same thing with Coca-Cola. Don't worry, it's only beer. They sell 6. The idea is to commercialize. Try to make drink more, no? 6 bottles you will buy, you will consume it faster than buying 1 at a time. That is the concept, commercial concept of driving the people to buy more and more. So 2 in 1. Similarly, muxes are 2 in 1. These flip flops are 2 in 1. So anyway, I have to buy a 2 flip flops and then a 3rd flip flop. I need to buy 2 chips. So, you can as well buy a 4-bit register, because register has a common clock for all the flip flops and 4 inputs and 4 outputs. That is what I want. I will not use. See, sometimes you think you are saving by buying 3 flip flops, you will end up saving if you buy a 4-bit register, correct? I told you this several times earlier. Anyway, so all I have to do is to program this ROM as per this table. So, present state, the address is, first address is 0, I told you generally written in hexadecimal. So, the PROM table or the ROM content table as they call it for this exercise ROM content table will be address content both in hexadecimal. So, I can write 0, 1, 2, 3, there is no need to see the, because it goes from 0 to F. Very first is 0, 0, 0, 0, last was 1, 1, 1, F. So, the first word to be stored is, in the first word 0, 0, 0, the word to be stored is 0. Second location I need to store what? 0, 0, 1, 0 is hexadecimal 2. This is hexadecimal 4, hexadecimal 6. Tell me quickly, content 0. Somebody can read it for me. 2, 4, 6, 0, 8, 0. I will up to, where did you go up to? Up to this we will read and then we will write one more column. So, 9, which is 9? This is 9, 6, 8, 0, 9. Okay, this is what? This is 4, 5, 6, 7, 0 to 7. Is that right? 8, 0, 9 is 7. So, I will write from 8 here, continue this table on this side, continue 8, 9, A, B, C, D, E, F. So, after 7 what? 7 is 9, for 8 it is 6, 8 is 6, correct? Then 9, don't care, so be careful here. How do you put a don't care in a ROM? How do you give a value and put it? I can't write a don't care into a ROM. So, that state, because an address which is physical address, this is an address, I have a ROM, I give an address and the output comes. Supposing whether a state exists or not, suppose I give an address, corresponding word should be read. So, I have to, so I can make all of them same, because whenever any of these states occur, which is not going to happen, I can always say the next state is 0, 0, 0, something like that I have to decide, 1, 1, 1 maybe, anything. So, whenever a state occurs, you put it back to a state which is existing in the circuit and usually the reset state. So, for the rest of these don't cares, I will put 0, 0, 0, output is also 0. So, I will fill all the columns, all the rows from here to here. Actually, there is a mistake here. Totally how many? There are only 8, 5, 10, you know, right? No, there is no mistake, 10. Up to 10 rows, there are addresses which are valid. From 11th to 15th, the next 6, how can this be? 10th to 15, from 10 to 15, 6 rows, there should be no output, correct? So, I will have to put a 0, I can put 0 all through. This is called the ROM content table. So, take a ROM of this size, 2 power 4 times 4, get a ROM programmer from somewhere, PROM programmer from somewhere, insert this PROM into your from programmer and get each word and the corresponding content. Put 0 0 0, first put a 0 address, put the content as 0, increment the address by 1, put the content as 2, increment the address by 1, put the content by 4 and finish the programming. Then connect it to the flip flops as you show here, as shown here, the circuit works. So this is again an MSI based or LSI based implementation. LSI or MSI here, because the ROM size is too small, I don't want to call it an LSI. Usually ROMs and PLAs, PLs are classified as large scale integrated circuits, but then the size here is so small. Doesn't matter actually, these definitions are not important. Implementation scheme is more important. How elegant it is, one chip ROM, appropriate size we have, program it, one register with 4 bits and a clock, that is it, give X and output comes. Again convert this into programmable array logic, programmable device. So this PROM is a programmable logic device. The next programmable logic device is what? PIL. For PIL I need to go a little bit into the thing, I am not going to do it, I am going to leave it to you as an exercise. What will be the size of the PIL? Four inputs have to be given and 4 outputs need to come. To this we will connect I am not going to tell you what is the only thing you do not know is how many minimum number of min terms, product terms can you have and reasonably. So determine the programmable logic PLA table, that means you go for minimization of each of these variables A plus B plus C plus and C. Each of those 4 columns you have to minimize with as many common terms as possible. Then come out with a list of product terms you need to generate and generate those product terms and combine them with the OR gate. And then you can use a programmable array logic also, we will see how to do it in the next lecture.